Yes, hello students. In my previous lecture, I explained the chopper that can be used for motoring operation of a DC machine. The energy in that case was flowing from source to the motor. Now, if you want to stop the motor or you want to reduce the speed of the motor and you want to send back the energy stored in the system back to the source, then you have to use another circuit that is known as this step up chopper. So this is a motor. This was earlier being operated by some step down chopper that we discussed in the previous lecture, and the machine was operating as a motor with the back EMF E slightly less than the voltage V, and energy was flowing from motor to from source to motor. Now we want to send back energy from this low voltage source E. E is less than V. So we have to send back energy from this low voltage source E to a high voltage source V. So that is the problem. So for this we use this circuit that is nothing but a step up chopper, and you can see how this operates. This whole operation can be divided into two intervals. One we call energy storage interval and the other is energy transfer interval. So how it is done? You have to operate this switch. Again, S is a switch which is fully controlled switch like MOSFET or BJT or IGBT. So when you give the signal to it, it will turn on, and when we remove the signal, it will turn off. So what we have to do here, we have to give a signal like this. So during the on period, T on period, we give the signal to the gate or base of this transistor, and for the remaining period, T off period, we have to remove the signal so that the switch is turned off. So when we give the signal to the switch S and S closes, then what happens? That interval we are calling energy storage interval. Let us understand it, how it works. So when we close the switch, the current will start flowing in this direction. The only voltage source here is the back EMF, and this releases energy. So you can say that the energy stored in the mechanical system of the motor is being released. So speed will decrease and the energy will be released. So this energy will and current will flow like this, and this energy released will be stored in the inductance. Inductance is energy storing device, and a part of energy will be dissipated in heat in the armature circuit resistance. So current will flow like this, and of course when energy is released by this motor, and the current will increase. So current will increase from some value IA1 to IA2 during this interval, and energy will be stored in the inductance. So as the current increases, energy stored in the inductance half Li square will increase. During this interval, you can say that as switch is closed, voltage here is 0, so VA will be equal to 0. So armature voltage will be 0 during this interval. So this is the waveform of the armature voltage during this energy storage interval. So during this interval, energy is not being transferred to the motor, rather it is stored in the armature circuit inductance. After this time, we remove the signal from the switch S, and during this interval you can say that in the previous part the diode D remains in the off state because this is closed, and the voltage appearing here is the reverse voltage applied by the voltage V. So diode D remains in the off state, it doesn't conduct. So this part of the circuit is out of the circuit. So energy only released by the motor and being restored in the armature circuit inductance. And the polarity of the voltage across inductance is also shown here. It is like this. Current is rising, so this is positive, this is negative. Now when we remove the signal from the switch, then what happens? That the current will now start decreasing. It was increasing, so it will start decreasing because we have interrupted the switch. and when the current start decreasing, that is dIA over dt will reverse. So polarity of inductor voltage will reverse. So it will become opposite to what it was in the energy storage interval. So you can see that the polarity of this voltage is now like this. Now this voltage plus this voltage, that is back EMF plus voltage across inductance, both combined will become more than the magnitude of this source voltage, slightly more than this, and that will make the diode forward biased. So current will start flowing like this through the source. So current flows like this. Energy is now being released by the motor as well as the inductor. So in the inductor, that stored energy in the energy storage interval will now release energy now, and both the energy from the motor as well as the inductor will be fed back to the source. A part of energy, of course, will be converted into heat in armature circuit resistance, and the remaining energy will be sent back to the source. And when this happens, then the current will start decreasing. The total voltage now in this circuit is equal to E minus V. So the voltage is there, current will start decreasing. So during this interval, energy is transferred to the source, and you can see that when this happens, the voltage available across the armature will be almost equal to supply voltage. Minus, of course, it is slightly more than this because of this voltage drop here. So this is the voltage will be V. So you can say that the armature voltage will be like this. So this waveform of armature voltage is like this, and current falls from the maximum value IA2 to minimum value of IA1, and it is tried that inductance is kept high so that conduction is always continuous. So now we can go for steady state analysis of the chopper controlled DC drive, both for motoring operation as well as braking operation. Now let us do the steady state analysis of chopper controlled DC motor. First let us see the motoring operation that we discussed in the previous lecture. So here the voltage across the motor was varying like this during the duty interval when the switch was closed. During the time delta t 0 to delta t, the voltage was equal to V, and when the switch was turned off, the voltage was equal to 0 and the diode was conducting. So in that case, the average voltage that appears across the motor will be equal to average value of this waveform. So V into delta t, the area under this curve, divided by the total time period. So V into delta t upon t, so it comes out to be delta V. That is, for delta equal to 0, that is when the switch is never closed, voltage is 0, and when delta is equal to 1, that is switch is permanently closed, the voltage is equal to V. So the average voltage can vary from 0 to the rated voltage or the source voltage. So this is the variation. So VA varies linearly with the duty ratio delta. Now you can think that a voltage source of delta V is connected across the motor, and you can simply apply those previous knowledge. How we analyze it is simply to write the Kvl equation for this equivalent circuit. So delta V is the voltage across the armature, average volt value, and RA RA into, say this is the back EMF E, and IA is the average value of current flowing through the circuit. Applying KVL here, you can write delta V equal to E plus IARA. You can write the value of current IA. So average value of current can be easily found. You need not to write the equations for IA1 and IA2 that we did earlier. You simply need to know only the value of delta. So delta V minus E upon RA will be the average current, and E will be known for a particular speed. For example, if speed is known to you and you want to know what is the corresponding torque. So in that case, this Q omega M is the back EMF that is known to you. So delta V minus E upon RA, you can find out the average current flowing here. Knowing IA, you can find out what is the torque K into IA, and knowing this, you can write the equation for speed relating the torque. Omega m equal to V upon K. In place of V, now you can write here delta V, average voltage, minus RA upon K square into torque. So the characteristic of the DC motor can be plotted like this for different values of delta. This may be for delta equal to 1. This will be for delta equal to say 0.75, or and so on. For different values of delta, you can plot the characteristics of the motor. Now for regenerative braking, we have seen that the armature voltage was 0 when the switch was closed. Switch was connected across the motor. So when the switch was closed, voltage was 0, and when the switch was turned off, then the voltage across the motor rises to V. So this was the situation there. Again, let us try to find out the average value of the voltage. So it is V area under this curve, that is V into T off upon T. So now you can define delta in different way. Delta I have defined here as T off upon T. In the previous case, it was defined as T on upon T. Now here it is defined as T off upon T, and you can take a general definition that delta is the duty period, that is energy transfer period upon the total time period. So in this case, during this T off interval, the energy is being transferred. So this you can say that energy transfer period upon the time period. So in that way, and both are same. So delta in here is T off upon T. Now the current that is flowing now here is delta V minus, as per this the equation, average voltage minus the back EMF upon RA. Now you can see that current here is negative, that is current is flowing back from motor to source, because in this case E will be more than this delta V, and the current will be negative. So this means that the torque will also be negative, and you can write the speed, the direction of omega m like this, and the equation is identical, and you can plot the characteristics for different values of delta like this. So analysis is very simple. We shall take up some problems that will make the things clear. How to find out speed corresponding to a torque or torque corresponding to a speed. So we can do it very easily. So that is all for chopper controlled drives. Now in the next lecture, I will try to solve a few numerical problems, and then we can compare chopper control and rectifier control. So that is all for today. Thank you.